Hello! In my previous videos, I've always talked about doing a bidirectional buck-boost converter to replace my current battery pack, which is made up of retired truck batteries that have aged. They're starting to fail. I'm getting a lot of really high resistance, so they're not very good anymore at producing power. It's okay for the testing that I do, but we really would like to improve on the battery pack in general. I've been wanting to build a bidirectional buck-boost converter around this guy. This is an inductor out of a Prius. It's very big. You should be able to handle the current. And we're going to do a little design here and figure out how we're going to do this. So the first thing, we're going to draw this, this inductor, because that's what we've got. So we've got this inductor. We don't know the value of it. We don't know how much current it can handle. Tried looking it up, can't find it. However, with a little bit of Wikipediaing, we should be able to find out everything we need to know about this. And we can measure it and figure out what's going on there. So for a bidirectional buck-boost converter, the first thing we're going to do is build a boost converter, because we want to take some battery voltage and generate a much higher battery voltage. And be able to do that. And for bidirectional, we want to be able to take this high voltage and convert down to a lower voltage to charge a battery, a smaller battery pack, and allow us to test things like motor controllers and be able to regen and hook up battery chargers and actually be able to test those under full load. So in this design, I'm looking at, I want to have it run off of 48 volts. And it wasn't just kind of arbitrarily picked. It happens to be a decent voltage. It's only 4 12-volt batteries. You can get a few lithium-ion batteries together. You can come up with the 48 volts pretty easily. So we want this to be a 48-volt DC supply. And on the other side of this, we need to have the boost converter. So we're going to use some IGBTs that I've got out of a UMC 440 controller that has died an untimely death. I've got it sitting over here. I'll show it here in a second. So we'll go ahead and draw out our IGBT. IGBTs are different than MOSFETs. It's pretty much a hybrid between a bipolar transistor and a MOSFET. So it's got the gate of a MOSFET and the bipolar transistor part of a regular transistor. And Back in the day, these were what if you were doing anything high voltage, this is what you had to use. Nowadays, with silicon carbide MOSFETs, you can get 1,000-volt MOSFETs without a problem. But back when these were made, that was pretty much the only game in town. It usually came in like 300 volt, 600 volt, 900 volt, 1200 volt. They seemed to go in 300 volt increments. The difference between say a MOSFET is that it has an RSD-on, which is a resistance, whereas an IGBT has a fixed voltage drop of 1.2 volts, 2 volts, somewhere around in there. And so that's why they're more efficient at the higher voltages, because you got that fixed voltage drop no matter what current, whereas the MOSFETs are more efficient at high currents but low voltage, because then you just have to deal with I2R losses, if that makes sense. So what we've got here is an IGBT. We're going to draw another one up on top of here. We'll go ahead and hook this up, and so it'll come way out here so I can make sure I got enough room to draw everything. So I have a capacitor. And on this side we'll also have a capacitor. Put it in here. So what's going on here is, came out terrible. There's also a couple built in the IGBT modules. You'll have a diode here. So I'll go ahead and draw those in. And so this is pretty much the basic schematic. This is how it works. We got a capacitor in series with it. This is the output side. This is the input side. So we're going to take our 48 volts. We're going to turn this IGBT on, And when we do that, current will flow through this inductor, back to the battery. We'll store energy in a magnetic field in here, and when we turn this guy off, there's nowhere for it to go except through this diode, and then we'll start delivering energy on this capacitor. So every time we turn this guy on, we're going to pump this little capacitor over here a little bit more, and we get voltage going up, 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 up. When we have a load on here, that's going to start taking away from that voltage, and so we'll have to increase our on time in order to get that voltage to maintain. Say I tell it I want to put 144 volts. We're going to have a microcontroller. It's going to read this potential here, or the output. It's going to fire this IGBT in order to maintain 144 volts. Now in the event that you're regenning, so you've pulled a bunch of current, you've spooled up your motor, and you start regen braking, that's going to make this 144 volts that you're targeting, this will start going up. You know, you get 150, 160 volts. And when the microcontroller sees that, it's going to stop firing this guy, and it's going to start turning on this guy. And what that does is current will flow this way through this IGBT. Can't go this way because this guy's off and the diode's blocking, so we got to go into the inductor. This capacitor here will resist a quick voltage change, so as that voltage starts going up towards like 60 volts, because we want to charge this battery, we'll start approaching 60 volts. We're going to turn this guy off, and the energy stored in here as a magnetic field will then complete the circuit through this diode here. And so that'll allow us to bidirectionally pump energy from this side into the battery, and vice versa, pump energy from the battery over to here to any arbitrary voltage, from 48 volts up to, I want everything to be rated at 600 volts. So this is going to be 600 volts. The IGBTs are going to be rated at 600 volts. This cap, probably 100 volts or so. Values, don't know. We've got to go look and see what's available. I don't have any 600 volt caps laying around. This probably we can get pretty easily. I think I have some 100 volt caps laying around. So we've got all that going on. One problem, if you look, is when these are both off, so nothing's happening, this 48 volts from the battery can come through the inductor, through this diode, and out here, and then return back to the battery. That means that even with everything off, we always have 48 volts out here. We don't really want that, so one of the things we're going to have is a line contactor. So we're going to put in here a good old-fashioned line contactor, and then we'll have a coil, right? And we'll control that. So we've got a line contactor here, and we also want a line contactor out here simply to be able to charge up, like actually we want this cap on this side, so it'd be out here. And then this is going to be ground. So we want to have our line contactor out here, right? So we want to be able to control that. We got a line contactor out here for our output. So we'll draw a connector of some kind out here. And then this connector can be for the motor controllers to plug into, or battery chargers, or whatever, whatever we want to. The device under test would go there. And that'll allow us, so the other thing is I want is like an emergency abort button that you can press, like a mushroom switch, so we'll draw that in here as a, one of those big red abort buttons that you can click to just drop everything out. So we got that. The other things that we're going to need is, suppose I got a battery charger out here, right? And 3.3 kilowatt battery charger, we plug it in, it's going to start charging. This battery can only take so much before it's fully charged, and we start having problems. So we kind of need a way to dissipate some extra energy, and the best way to do that is, we can do a, let's put a resistor here, and because this is going to be the low voltage side, we can get away with just a regular old-fashioned MOSFET here. So this will allow us to go ahead and discharge not only discharge the battery, but if we get above a certain voltage, we want to protect the battery, we can start conducting through there. I had a calculator down here somewhere. I don't know where it went. But, I'm not quite sure where that went. Yeah, gonna be a little difficult to do math, but let's just see here. So we got 48 volts, and we need, say, something. I mean, if we were doing a 3.3 kilowatt battery charger, we're gonna need something rated around 4,000 watts. And you're like, well, that's a really big resistor. They're actually not that big. You can get them, if you go on eBay and search for a dynamic braking resistor, you can get some decent sized resistors. I saw a couple on there for that were an ohm each at 2,000 watts. So this ends up being 0.5. So if you're doing 48 volts divided by that, you're looking around, 96 amps or so. So it should be able to be okay. I mean, plus the resistance of this would be pretty low. So yeah, as the voltage gets up above a certain point, our micro is going to be reading the voltage, and then we're going to turn this guy on to prevent this overcharging this battery and just to burn up everything as heat, and that'd be pretty big. Now, one of the other things is we kind of need that on the other side as well, and that's because if we've got current flowing through here, so say I'm boost converting to 450 volts for a one of the UMOC high voltage motor controllers or DMOC drives, and we've got current flowing out of here through this inductor, right? And we're building up, say, hundreds of amps here, about 100 amps or so, right? And when this guy turns off, this energy goes into here. But say my motor controller that's hooked up has its contactors clicked out, or it had an error, or its fuse blew or something like that. There's nowhere for this energy to go. It's going to hit this capacitor, rapidly charge it, because we're talking hundreds of amps here, right? Rapidly charge it up. We're going to exceed 600 volts. We're going to break that. We're going to break our MOS or our IGBTs. We're going to break everything. So we need essentially the same thing we've got over here. We'll use this one since I drew it in. We want another resistor here, and because we're on the high voltage side, we'll go ahead and give this an IGBT. Just for good measure. And of course, I didn't draw it, but this MOSFETs have the body diode built in them too. So we'll turn that on. So essentially, if the voltage here, so what we want to do is have some kind of comparator to go with, and say, hey, I'm commanding, say, 144 volts. If I ever go above 160 volts, like I'm regenning a bunch, or I got a battery charger hooked up, something crazy, we want to set this up pretty high to protect the system. Well, for example, like 450 volts, because that's closer to our where we want it to be. So if it gets above 500 volts, we want this guy to turn on to dissipate that energy. How big does that need to be? I don't know. I got to do some math. I got to figure out what this inductor is, how much energy it can store per cycle, which would be based on my switching frequency and all that kind of stuff. And once we know that, then we can size what this resistor would be. So we've got that. The other thing we need to do is we'd like to know about current. So we want to have a current sensor. We want to know how much current is going into the battery and how much current is going into the load. So in order to do that, we want to we'll just slap a current sensor. Kind of ran out of room here. We'll just call this current. So we got a current sensor there, and we want a current sensor here. So we got input, and we got output. Right? So we got that going on. And the other thing is, for this, I want to have, this circuit right here is also useful. You see me every once in a while working on a battery charger or motor controller. I stick a little resistor on, one of these resistors, one of these guys, to safely discharge the device under test so I can take it apart. And by having this hooked up, we can do that. We turn everybody off. We can just discharge the voltage that's stored on the device pretty easily. Just dump it. So that'll be useful. Could also just pump it back over until it reaches 0. That works too. Either way, so we can do that. what other cool stuff can we do? I think that's about it. For these IGBTs, we're going to need gate drivers. We're going to steal them off of this UMOC445 here. I'll show you that in a second. We'll just draw them as little boxes, gate drivers. And then we're going to come in from the micro with PWM. And same thing over here. And yeah, other than that, shouldn't be too difficult. Should be able to get it done. Might even be able to do proof of concept today. We'll see what happens. But yeah, that's is going to be the bidirectional buck boost converter. To control everything, probably going to enlist the help of the old DMSC adapter. Can already control contactors, so we already got that built in. It's already got isolated power supplies, which lets me power everything. We've got Wi-Fi on it, so if we want to do a display or a interface, that's pretty easy to do since we already got that. And we've got all this extra I/O that's floating around on here. That's more than capable. Like this whole port is port E right here is all the PWM signals, so that's a very easy. Micro has built-in PWM engines, and that easily handles all of these. So we got at least 4 PWM signals. Not a big deal. Totally can do that with this. So we'll probably write some code for that and get that working. And other than that, I can show you that I've got this UMOC445 controller here that has died a horrible death. So those current sensors I was talking about, I got 2 right there. So we're going to salvage those from this. You might be asking, oh, it's a UMOC445. That's a perfectly good controller. Why are you going to sacrifice one to build this? Well, this is the processor board from it, and it met an untimely death. The 12-volt regulator on it, or the 5-volt regulator died, and I let 12 volts go straight through to everything. And so when I was working on it, I replaced the 5-volt regulator with a new one. I, of course, hooked it up, and the output is dead shorted, you know, and one of these chips got really hot, so I unsoldered that guy. The next chip got really hot, so I unsoldered that guy. You know, the 5-volt supply is being held down at like half a volt, so obviously something's still shorted out. So after replacing both of those, the next chip that got really hot was the micro. And at that point, it's really not worth repairing. It's just dead, because you know every single chip on here got exposed to 12 volts, and they're all probably dead. So, I mean, I don't have the code for this, so I can't replace it. And then we've got PLCs and PALs and stuff on here that are just, you know, I don't have the code for that goes in those chips either. So that's programmable, that's programmable, that's programmable, that's programmable. I just don't have that code, so the loss of this drive, yeah, it's just going to become, the other parts are working, the rest of it, so we'll end up with that. And that's what we're going to salvage the parts out of from this guy right here. So, probably not going to use this contactor. I know I drew contactors on there, and the reason is, if you look right here, it's 180 volts, and we don't have 180 volts in order to run that, and I don't want to do another boost converter just get 180 volts to turn this guy on. Plus, I can salvage this and use this as a spare for repairs. But we are going to use these IGBT bricks. They are made by Mitsubishi, CM400DU-12F. Very large. I can pull up the data sheet on it. So we're going to use those guys, and we're also going to see this little SIP in here. That's the isolated gate driver. So we're going to pull that off of this board as well. We can't use anything else on here because, again, this board is designed to take, you know, something 300, 600, or 300, 400 volts in to generate all of the isolated supplies to run all these guys and run everything, and we just don't have that high voltage available, so you can't use the contactor. We're not going to use anything on here. We're just going to use the IGBT brick and these little SIP gate drivers. There's 6 of them in there. The other cool thing is we've got this big heatsink, so we'll use that, which is probably just unbolt everything from it. Just use one brick is all we need. This has both that high side and low side IGBT in it with those catch diodes, freewheeling diodes. Everything's already built in. So that is the plan. So you're going to have to... my goal is to fit everything back in the actual original case, which would be really cool. Then it'll all be nice and everything will fit. So let's see here what would be next. So if I go ahead and turn this on. So we got this inductor, right? It's out of a Prius, and I believe it's a 2nd gen Prius. So this XW20, which is 2003 to 2009. So I think that's what it is. But if we look at what, so for the electric, they run 50 kilowatts. So we got 50 kilowatts. And if we scroll around in here, we talk about the battery, and right here, battery is about 200 volts. So if you do 50 kilowatts divided by 200, you get 250 amps. So we know, because they're taking the battery and they're boost converting it up to, I think, 500 volts or so. I think it's added over here. Yeah, 500 volts. So we're taking this 50 kilowatts, boost converting from 200 to 500 volts with this inductor. So we know this guy is capable of at least 250 amps. So that's useful. So we know that this inductor is at least rated for 250 amps. It's probably rated for more, because if you look at that battery, it was the nominal voltage. So when it gets low, it's obviously going to have to pump more current. You might be asking, why did the Prius use a boost converter? If you drive a electric vehicle, you definitely know that as your battery discharges, performance is definitely less. And the Prius has a very small battery pack in it. It's not very big at all. And so it's only really good for like one acceleration, then it's pretty much depleted and it has to get recharged. And at the end of that acceleration, the voltage would be really low, and that's when you need it the most, is at that higher end. So what they do is they boost convert that 200 volts up to the 500 volts and then power the drivetrain with that, their motor controller with that. And that allows them to, as the battery voltage is coming down, they're maintaining that 500 volts all the time, so you don't suffer any performance decrease. So what happens is at the top, you know, you're decreasing, you know, it decreases more rapidly as you get to the bottom until it's depleted. And same with regenerative braking. Since they're maintaining that 500 volts, as your battery recharges, it can maintain that the same opposite. Like if you're driving a electric vehicle and your battery is fully charged, you know that regen doesn't work as well. You get that squeal, and that's the motor controller kicking in and out because it's saying, hey, I'm outputting too high a voltage. And so it trips in between. So that's why they do it, is that, and it allows them to have a smaller battery pack in there, so with less batteries. But yeah, so there's that. Here's the IGBT that I was talking about. They're apparently $210 over at DigiKey. My aim is horrible. There you go. So this is that module, PowerX, also Mitsubishi, although this does say PowerX. Pretty sure it's made by, PowerX might be owned by Mitsubishi, because the ones that are in here actually have Mitsubishi on them. Anyways, they've drawn their schematic kind of convoluted. If you were to take this one and rotate it like this, and then take this one and rotate it like that, then you would have the IGBTs in the same orientation that I drew it on here. We have the two like that. I leave that as an exercise to the viewer. I don't know why they drew it that way. Makes it kind of hard to see. But I guess they drew it the way it physically is in the module. But anyways, the reason I bring this up is, 400 amps, 600 volts. So if this guy can handle at least 250, maybe 300 without a problem, IGBTs are going to be good. I'm not going to worry about that. Built-in catch diode. Diodes are good for the freewheeling. They call it in here. They call it freewheeling, super fast freewheeling diode. And somewhere on here they'll tell you about the diode. Somewhere. Anyways, the diode's good too. I believe it's also good for 400 amps. Except I'm not seeing it on here. I thought it was in here somewhere. Oh, it's okay. It's in there somewhere. For some reason, I'm just not seeing it. Oh well, I can't find it. It's also good for 400 amps. Maybe it's just in one of these graphs somewhere. But anyways, so we've got that. And then that little gate driver is made by these guys. This is it. And you can see it's already completely isolated. So all you got to do is turn on this LED and it takes everything else. Now it needs both a, I didn't mention this, but IGBTs require a positive and negative voltage in order to switch. Well, they can switch without the negative voltage, but it makes them switch faster if you slam it with plus and minus. And you can see their little thing where 0 volts is definitely going below. And if you look at their recommended, they're saying they want typically 15 volts and then between -7 and -10 volts for that. So we'll have to generate some supplies that make a positive and negative isolated supply for each of them. Although I've got, give me one sec. I was going to say I got a bunch of these, but they actually are only 12 volts, so not quite enough. DC to DC converters, but it's 16.8 to 75 volts, so they're designed for 48 volt input, but they only put out 12 volts. And I don't know how much isolation they can handle. I probably picked these up at the Dayton Hamvention, although I probably didn't pay 20 bucks for them. These are just little DC to DC converters that I have floating around. But yeah, these should be pretty easy to control. I just gotta get those supplies and probably just generate a plus or minus 15 volt supply and then regulate the negative side to like 9 volts, negative 9 volts or so. So yeah, that's got that, and yeah, I guess that's about it. Oh, I know one thing we could do. This inductor, we need to figure out. So we know we need to know what the inductance is in order to do some math on it, and we definitely calculated out how much current it can handle, and we can do this really quick. So I'm going to go ahead and hook this up to my function generator, and so we've got the inductor hooked up, right? And a neat thing that you can do to calculate inductance is simply we're putting in, so we want to look at this voltage here, and we want to give that just enough amplitude. We want to get it to halfway, and if you get halfway, So we'll go ahead and turn this down and see it's starting to attenuate the waveform. And when we reach halfway, like right there, that tells you what the frequency is, and then you can use that in an equation in order to calculate it, and that equation is L equals 1/3 square root of that R over 2 pi f. And R is from the function generator, and we know that to be 50 ohms. And thus, you end up with 4.57 over f is equal to L. And if you work that out, put the frequency in there, that equals 371 microhenry, where f was 12,300. And there we go. So now, once we know that, we can go ahead and plug this in, and we know 371 microhenry. And I'm going to end the video really quick because it's about to run out of recording space. So thanks for watching.